Today, myself, Chelsea Smith, and my colleague Harriet Branson will be talking through our chapter Conservation 1, assessing the spatial relationship between burned area and precipitation of the cloud-based remote sensing with Google Earth Engine Fundamentals and Applications book. Harriet and I work together at Fauna and Flora, the world's oldest conservation NGO. Fauna and Flora deliver conservation projects on the ground in over 40 countries across more than 120 projects. Harriet and I, alongside the rest of our team, provide geospatial support to collect, manage, and analyse data to help inform conservation projects. Today, we'll be talking through how one aspect of remote sensing helps us do that. In this session, I will provide an overview of the chapter and touch on some theory before Harriet will talk through the script and provide an in-depth tutorial of how we analyse fire and rainfall. The goal of this session is introduce the need for fire activity and rainfall trend monitoring to inform conservation management practices and how we do that. The learning outcomes are understanding why fire and rainfall trends are so useful in conservation by creating a time series of burned areas and writing a function to map aerial mean rainfall calculations over an image collection, as well as generating an interactive graph displaying fire and rainfall trends over a 10-year period. We assume you know how to import images and an image collection to filter and visualize this data, and also how to create a UI chart. We'll also assume that you know how to summarize an image with the reduce region function and create a function to map it over an image collection, as well as being able to work with chirps, rainfall data, and mask cloud shadow, snow ice, and other unused pixels. The chapters that you might want to refer back to, if you're not quite sure of any of those, are also listed on the screen now. So first, let's go over some theory and explain why we're so interested as conservationists in fire and rainfall trends. But first, globally, biodiversity is under threat from changing climates, habitat loss, and fragmentation. Conservation work to protect, manage, and restore ecosystems is vitally important to maintain global biodiversity, which supports climate regulation and a host of other ecosystem services on which we depend. Ecosystem services include things like the nutrient cycles, which help us grow our food, fresh water provision, and environmental structures, which help us build our societies, all of which are affected by fire and rainfall. We rely on nature every day of our lives, and it is currently under threat. But the work we do at Fauna and Flora alongside our partners is working directly to benefit nature on the ground, where we can have the most impact. However, to deliver conservation management on the ground, we need to understand the landscape in which we are working in. Remote sensing offers a valuable tool to collect, analyze, and display data over an entire ecosystem, allowing us to cover and glean insights over a much wider area than would be possible with ground observations alone. Environmental variables such as fire and rainfall have direct impacts on habitat and forage availability. Monitoring of these variables can help inform conservation, such as fire management to reduce the severity of fires and amount of habitat loss. Tracking the severity and spatial dynamics of fire coverage, for example, can help our teams identify where controlled early burning, the practice of burning off some fuel out of fire seasons in a controlled way, could stop more severe, uncontrollable fires breaking out during the fire seasons. Monitoring rainfall patterns can help conservationists understand the climate conditions species prefer in their habitats and if the conditions are at risk of changing. Determining the species preferential habitat conditions can help us build species distribution models to understand the species range across the landscape we're working in, and also identify if that species range is at risk of shifting or having to move due to shifting rainfall patterns with climate change. In this chapter, we will see how using the Earth Engine platform allows conservationists to scope fire and rainfall conditions for any site using global datasets. The data we visualise today is being directly used in real-world conservation by fauna and flora to inform fire management, as well as indirectly through the identification of climate conditions to which species are adapted. Before we move on, just to note that if you want to follow along with today's tutorial, you need to open up the repository in Google Earth Engine and access the script in this way via the link on the screen now. I'll now hand over to Harriet to talk through the script and the work that we do in more detail.
Hello everyone, and welcome to the practical part of this Google Earth Engine tutorial for Chapter A3.9 Conservation I, Assessing the Spatial Relationship between Burned Area and Precipitation. In this part of the tutorial, I'll walk us through the different purposes of each code checkpoint, and after each section, we'll go over to Google Earth Engine and look at the code in a bit more detail and run it together. The first step in the code is to upload and explore the area of interest. We've used northern Mozambique's Nyassa Reserve, which is home to 40% of the country's entire elephant population, and is also a haven for two of Africa's threatened carnivores, lion and wild dog. Fire is a key ecological process in forested savanna ecosystems, and these are prevalent in the Nyassa Reserve. So knowledge of the fire regime is a huge factor in forest fire management. Our area of interest has very stark wet and dry seasons. So when you first run the code, take a look at the satellite imagery base map, as that shows the landscape in the wet season. The next step in the code is to use the MCD64A1 dataset, and this is the MODIS burned area dataset. This is a global layer that represents burned area at 500-meter resolution from 2001 to present day. The layer is accompanied by a band name burn date, and that enables you to disaggregate the burned area dataset into daily fire data. So to do this, we'll first filter the MODIS image collection based on our time span requirements. So in our instance, we're looking at fire patterns over the past 10 years, but this could be adjusted for any temporal time study. The MCD64A1 dataset comes with three main bands. So these are burn date, uncertainty, and a QA band, which stands for quality assurance. In this case, we'll be only using the burn date band, which associates each pixel of burned area with a day of year value. Once we have this, we can create a function that will calculate the area of pixels associated with each day. The function is structured so it will map over each image in the MODIS burn date image collection. So it begins by using the command pixel area, which calculates the area of each pixel in square meters. To limit the calculation to specifically burned areas, which is what we need, we have to use the update mask tool with our input image as the variable. This is because we want our final area calculation to be relevant to the burned areas only. We then need our final area value to be in square kilometers instead of square meters, so it's a bit more understandable. And then so to do that, we divide by 1 million. The reduce region command gathers the sum of burned area within our input area of interest at this correct scale of our input image. So that's 500 meters for our MODIS burn date image collection. Once we have that, the get number command then recalls the area calculation per image per day of year, and then we append it as a new band on the area of image collection. Since the MODIS image collection has a very handy system time start embedded within each image, we can then select that area band and continue without the burn date band, as we know that the time and date value is actually embedded within each image and we don't necessarily need burn date. To show the total amount of burned area over the past 10 years, we can then plot this on a time series graph. So we define the X property, which is the X-axis, with our system time start for the date variable on this graph. And then we can plot the total area burned with time on the Y-axis. So we can take a look at this code now in a little bit more detail in the Google Earth Engine platform. So when you first open the relevant link for the script repository, you will see it load and open on the left-hand side of your screen. This repository, the projects /geeedu/book, holds all the scripts for the entire Google Earth Engine tutorial book. But the link that you click should automatically open the relevant chapter, as we can see, A3.9 Conservation Applications and our 3 checkpoints. So if you navigate towards the A39A checkpoint, you can click to open the file. It's important to note at this point, if you need or would like to make edits to this code, please do, once you've edited, click Save As and don't overwrite any edits in this repository. So as previously discussed in the first part of this tutorial, we upload our area of interest. So in this instance, we've used coordinates to create a bounding box, but you could also upload or draw your own polygon. We then use center object. So this allows us to rearrange the map frame so that our AOI is in the center of the map. The next section of code is map.addLayer. So this allows us to add the layer into the map frame. So as you can see, we've done the color white and it's added into the center of the map frame. We then move over into monthly burn date area. So as discussed, we add the image collection and we filter this based on our time span requirements. We then select the burn date band using dataset.select, so picking out only that band from the image collection. We then have our function here, which calculates the area of pixels in each image by date. So we're using that function update mask to limit our area collections to the burned area data. We're dividing by this 1E6, which is 1 million, so that we have our output in square kilometers. We're clipping this to our area of interest, so this box specifically, as we don't need information outside our area of interest at this time. We're then using the reduce region to scale our process to the right scale for the imagery, so the 500 meters. And then we're also getting and using that get number function, as we said, to pull that area calculation and then append it to the image collection with the band named area. Once we've created that function, we then apply this to our image collection. So as you can see here, we're creating a new image collection called burn date area by applying the add area function. Once we've done that, we can just select the area band, as we have the system time start function that gives us the date values. And so we don't necessarily need to keep that burn date band. So we're just pulling the area band out. We can then create a chart that shows the total burned area over time. So using the UI.chart function, we can pick our image collection. So that's our burned area that we've just created here by pulling out the area band. We've got the scale, which is 500 meters, and our x-axis property, which is the system time start, so time. We've then set the series name as area, so that's our label for the legend. We've then got a bunch of basically formatting here. So we've got the title for our chart, we've got the date, the format of the date. So we want years only, so we've done quadruple Y in all caps. We've got our grid lines, we have formatting on text and style, so in bold, yes, but not in italics. And then we have our y-axis, so the v-axis, which is vertical, and the h-axis, which is horizontal. And so we've labelled this our burned area. We've set our min and max values so that the bounds of the y-axis is appropriate for the data that we have. And we have things like line width and the colour of the chart. And then so we say, once we've finished this formatting for the chart, we can print our burned area chart. And as we can see, it's appeared in the console here. So once you've computed this graph, take a look at this graph in a little bit more detail. When you hover over your mouse at each point, can you identify which month has the greatest burned area? Does this vary year on year? What are the patterns like for burned area in the Niassa Mozambique Reserve? Going back to our slides, we can then move on to the next checkpoint. So section 3 is about looking at our aerial mean rainfall time series. So to inform habitat management and further understand the fire patterns within northern Mozambique, we have to also consider patterns of rainfall alongside fire. So to do this, we've got a great data set called the Climate Hazards Group Infrared Precipitation with Station Precipitation Dataset, and that's often abbreviated to CHIRPS. This dataset measures precipitation levels every 5 days from 1981 to present day at 500-metre resolution to make a long-term quasi-global dataset. First, we will define our temporal range. So we need to match our temporal range in the CHIRPS dataset with our MODIS burned area dataset. So that's from 2010 to 2021. And setting the advancing dates from these years. So after this, we create a sequence of years and months that can then be used to filter the dataset chronologically. And after setting these parameters, we then filter the CHIRPS dataset using the start and end date and sort chronologically in descending order using the same system time start property that we used in the previous section. We can then filter the bounds to our area of interest and select the relevant precipitation band from the image collection. Once we've filtered our dataset, we can then move into calculating monthly precipitation using a function. The function that we've written maps the input y over the list of years generated above. The function then returns the total precipitation for the month alongside a date variable and the system time start property. The command millis is used to keep the system number that refers to the date collected. Once we've run this, we can then print the image collection to make sure that everything's run correctly and it looks good. Once we have the monthly precipitation levels, we can then use a reducer to calculate the mean total rainfall across our area of interest, and that's known as the aerial mean rainfall. We can then plot these on a time series graph in a process very, very similar to what we've just done. So once we've got our graph printed, we can basically investigate it the same way that we have our burned area data set and look at perhaps how precipitation values have changed year on year and whether there have been spikes in rainfall or droughts. So following the same process, we can take a look at this code in a little bit more detail in Google Earth Engine. So once we've opened this, we can click to the A3.9 checkpoint and the script will open. So this, as you go through the checkpoints, they build on from the checkpoint before. So as you can see in this A3.9, we've also included the checkpoint from before to make sure it's coherent and you're following along. If you scroll down, you can see that this is the checkpoint here, where we get to the CHIRPS dataset. So we're at the second checkpoint. So as we discussed, we've loaded in the CHIRPS rainfall pentad dataset. We've defined our temporal range, so we've got our start year and our end year defined, and then we've set the advancing dates. So it's a little bit different from the MODIS burn date band in that we need to specifically set the years, days and months from our start and end year so that we can provide a sequence for the function to be able to understand when we need the data for and which dates we need precipitation for. Once we've filtered this data set based on our temporal range, so here you can see we're using that system time start property, we're filtering for our area of interest, and we're selecting the precipitation band only because that's what we're interested in. We can then move into calculating the precipitation per month. So this is that function that maps over y, which is our input, and we'll go over that sequence of dates that we just set and pull out our precipitation values. So using that millis to keep the system time number, calculating the sum for each month, and then spitting this image collection out once it has been processed so that we have monthly precipitation data within our area of interest for our relevant time period. And then following a very similar process, we're going to plot this on a chart. So using the UI.chart, selecting our monthly rainfall, setting our region, our area of interest, using that reducer to calculate areal mean rainfall, setting our scale to 500 meters, which is the resolution of the CHIRPS dataset, plotting our x-axis property, which is the system time start, adding the label for the legend, formatting the dates, adding our vertical axis title, so our y-axis label, setting the relevant bounds so we display the data correctly, and setting the line width and the colours, and printing our chart. So we can click run here and it will start running all of these. So in the console, you can see where your print commands come up. So here we have our image collection. So we have our different features. Here we can see we've got 144 elements in our image collection of all of these bands. And when you open them, you can see that we've got the different properties and we've got the system time start, which is the date number that refers to each band, each image. And then we've also got our month and year that we've added on here through our date sequencing. And here we can see the chart, and when we hover over it, we can see the different levels of precipitation in millimeters and how this varies year on year. In instance, in June, we're getting about 1 to 2 millimeters of precipitation. And in the wet season, so February, we're getting over 300, nearly 350 in the highest precipitation value in January 2016. So heading back to our slides, we can then move into section 4. So now that we have visualized these patterns in both burned area and precipitation separately, it's important to start putting these patterns and this data together to be able to understand how the data is interacting, what is the dynamic between fire and precipitation. So to do this, we combine the two image collections in order to plot them on the same graph. So once they are combined, we can then begin by creating a multi-variable time series chart. So here we're utilizing that system time start property that's present on both sets of our image collections. We're then able to plot each variable temporally very easily utilizing the system time start. Once we've done this, we can then set both series names and set interpolate nulls to be true, and that will fill in some of the gaps in our precipitation data to provide a continuous data set that can be plotted alongside the daily burned area data. To enable the two y-axes, we need to set some series parameters. So by defining our target axis index as 0 and 1, we can then set our vertical axes to match. So using two sets of parameters with different labels and different bounds for ease of plotting. This is really useful since the burned area and precipitation datasets have massively different minimum and maximum values. So it would be really difficult to analyse these on the same axis. You can then print the chart in the console for export if necessary, but we'll also add it to the map later to look at the data a bit more interactively. Once we've created our final chart that displays burned area and precipitation, we can then build some legends on the map for spatial data. So we'll use two different functions, and we can create a horizontal legend with a set gradient palette and custom markers that correspond to the precipitation data. Now that we have our legends complete, we can then add our double variable time series chart onto the map and center our map on our area of interest. Whilst visualizing data on a static chart is useful for further analysis and identifying patterns, it's also really useful to actually see the corresponding spatial data to a particular date or even a fire event. So to do this, we can add an interactive element to the chart. So in this code, we've written it so if you click on a particular point in the chart, it will reveal the corresponding image for burned area and precipitation on the map. To do this, we need to create a function that uses burned area and precipitation, BP chart, and executes on click, displaying the relevant data based on the input values. By utilizing the system time start property, we can query the date, which will then be used to identify the first image that appears within the list of images within the area of interest. We can then format the legend box within the map so that it shows the date and time of the layer selected. Following this, we can then set the symbology of each layer, so burned area in red and precipitation color gradient from a sort of light yellow to dark blue, and display that relevant layer with the date text string on the map. So it allows us to kind of see the burned areas and see the relevant precipitation. We then have this really useful interactive map in which dates, fires, or rainfall events can be queried and explored for the Niassa Reserve in northern Mozambique. So we'll walk through this in a little bit more detail in Google Earth Engine. So following the relevant link to the code checkpoint, following the link to the third checkpoint, A3.9 and then we can scroll down to the last checkpoint, which is here, combining the chirps, average rainfall and MODIS monthly burn. So I've highlighted all of these in comments so that we can go through this more complicated step by step. So to combine the two image collections for joint analysis, we're going to utilize the merge function in Google Earth Engine. So we're picking up this burned area dataset here, we're merging it with the monthly rainfall dataset, and then we're going to print this collection. So we're printing the merged image collection with the value. So burn, precipitation merged. So I'm going to click run. And you can see the other aspects of our analysis coming up here, and here we've got merged image collection, and we can see that we have 288 elements. We can then move into actually plotting these two time series on a graph. So we can just highlight this and uncomment it. So here we are creating this BP chart variable. We're using the UI.chart, but we're taking UI.chart image.series. So we're taking our merged image collection, setting our region as our area of interest, setting our scale, which is the same for both are at 500 meters resolution. We're setting our X property, so our X-axis property, which is the system time start, which handily is present in both data sets. So it allows for very easy plotting. We're setting our series name. So we've got burned area and precipitation. The chart type is a line chart. And then we're going through and setting our options. So as we said in the presentation, our interpolate nulls is true, as we want to provide continuous data. And in the precipitation data, there is inevitably some missing data. And so filling in those null values allows us to look at continuous data over the past 10 years. And in this plotting, as we talked a little bit about in the presentation, we're using two sets of series with a target axis to create the two y-axes needed for plotting. So we've got our 0 and 1. So we've got our first line and our second line, which is relevant for the burned area, and then the precipitation. And then being able to set these two as different colours is very useful for obviously identifying which line is which. We then set our settings for the horizontal axis. So we've got our dates, our year format. So as previously with our other charts, we're just using that quadruple Y so that we have just the year value like 2010. We then have our vertical axis setting. So again, utilising that 0 and 1 distinction. So our 0 is our burned area data set. So setting the label for the left-hand axis. And then 1, which is our right-hand y-axis, is precipitation, so setting the label for this. We then also use the curve type function so that we have a slightly smooth data set for easier interpretation. And then just setting our chart style with positioning and width and height. So we can run this now. And like I said, you can print this, like we said in the presentation, if you would like to print this chart and see it now, you can just print the BP chart. But in this instance, we're going to plot it on the map anyway, so we won't add it right now. We can then move over to creating our legends. So the first legend is our rainfall legend, and we've set our colour palette here, which is from a light yellow to a dark blue. We're then writing a function so that we can have like a little thumbnail on the map that shows from light yellow to dark blue and is relevant for the data set. So setting the size of the legend, the type, the min and the max, and then the palette, which we set up here, so the colours. And the stretch, so horizontal, is saying we want the colour gradient to be horizontal stretch underneath the values. We then go into actually formatting the values on the rain legend. So we've got the title of this little text box image that we're creating, so the total precipitation. And then we have the different formatting, so bold, horizontal, and then also the different labels. So we want a value at the start, the beginning, and the end. So we want 3 divisions in the legend so that we can understand what the values mean relevant to what colour. And then we just continue to set these values using the UI.label function to make sure that these are all formatted correctly and are in the right place on the legend. And then lastly, once we've completed that, we use the map.add function to actually add the values onto the map. So splitting these up correctly, adding the right colours on and printing it in the right place. We then go on to create the burned area legend. This is much more simple, as we've not divided it by date, it's just a red marker for where there was either a fire or there is a burned area in the landscape. So here we are adding this onto the map and setting the colours here. So once we've added the burned area legend onto the map, we can then recenter the map to our area of interest and add our burned area and precipitation chart. So we can click run, and once it's run, we can see that this is now generating. So this is our burned area legend. So you can see here we've got the red indicator for burned area and the right label. And then we have total precipitation in the wet season. So we have from 0 to 500 millimeters. As often in the wet season, it's going to be down here. So we've now added this to the map, and we can now see our combined chart as well. So you can see here we've got precipitation in millimeters on the right hand axis and burned area in kilometers squared on the left hand axis, and dates across the bottom. And then we have our legend for burned area and precipitation. And if you hover over each one, it will highlight the relevant data set. So now we can move into adding an interactive query to our data set. So this is the function where if you click on a certain point in the map, it will display the relevant burned area data set and the relevant rainfall data set for that particular date. So as we just said in the presentation, we're using the on-click function. So this takes the X value, the Y value, and the series name. And so we are setting it so it shows the layer for the date selected on the chart. So it equals, so we're using e.filter.equals to select the right value from that system time start property. We're then searching for that layer in the image collection that links to that selected date. So we want the first layer that comes up in the list when we query that. And then if something does come up, we clip it to the area of interest and we select the relevant date that we want to select. The relevant data set even. So we then create this image. So we have a burn image, which is this which utilizes that dot filter that will pull the data set from the equal date function that we've created, and then pulls in also the rain image and displays these on the screen. So converting the date value in the English date format, and then also resetting the map layers each time a new date is clicked. So taking away the old dates and then replacing them with the new date as you click through the graph. And then also setting the visualization here to make sure that it aligns with what we have in our legend. And then once we've run through all of this and make sure that we are pulling the right data set for the right time, depending on where the user has clicked on the graph, making sure that it's got the right band, making sure that it's overwriting a previous layer that was displayed, and then making sure that it's deformatted correctly in the colouring and the palette is appropriate for what we've previously set. We can then move into actually adding these layers to the map. So using these two variables that we've created, so classification R, so classification rainfall, classification B, so classification burn date. So those are these variables that we've set up here, where we're pulling those values from the image collection. We can then add this to the map. So we are adding the classification rainfall using the visualization parameters, and then setting the title to be totally monthly rainfall on, and then our date string, which we've just formatted above. So setting the date value to be actually a string rather than just a big long number, to actually have, October 2021 instead of one long uninterpretable number, and then repeating that for the burn date data set that we've pulled out from the list as well, and using the visualization parameters for the burn date, and then setting the legend title to burned area on relevant date string. So we can click run to rerun this, and I'll just pull the code away so that we have this full screen. And we can see that once it's loaded, we have our chart in the corner. And if I start clicking on some interesting points, it will start loading. So we have up here, we can see these loading, and we have total monthly rainfall on October 1st, 2017, and then burned area on October 1st, 2017. So we can see that there was very little rainfall on this day, but there was a significant amount of burn events or fire events in this time period. We can then also perhaps look at some really high precipitation. So back to that January 2016 value that we looked at before when we were identifying the highest precipitation value in our area. So here we can see that there is very, very dark blue. Looking at our legend, we can see that this is around 350 millimeters across our whole area of interest. And there are no red areas showing up, which means that there is no burn events for January 2016, which makes sense. If it's the wet season, there's a lot less likely to be fires. We can also perhaps look at how once that kind of interchange between going from the dry season to the wet season, how this might this transition might happen. So looking at how precipitation starts to increase or decrease between each season, and how that influences when fire events start. So for this particular value in November 2020, we can start to see the rain coming in our northwestern area in our area of interest, and how the burned areas are more towards the southeastern, and kind of looking at how this might impact some of the conservation management decisions that we have, or looking at how this might actually impact landscape dynamics. So going back to our slides, we can reflect a little bit on what we've learned in this chapter. So we started by creating a time series of our burned area dataset. We used the global MODIS burned area product to do this. We then utilised the long archival CHIRPS dataset to calculate aerial mean rainfall. And then we graphed total seasonal rainfall using the time series chart. We then moved into being able to merge two image collections to show two variables on one interactive chart in the Earth Engine map. So with the code that we've run through and learned throughout this chapter, you can now create burned and aerial mean rainfall time series for your own region of interest anywhere in the world. So I'd suggest trying to recreate this analysis in a different environment, perhaps considering extending the time series over a longer period, detecting any trends that are linked to rainfall and fire events, and whether this might actually impact any landscape decision making. Monitoring vegetation can also be extremely important in conservation and can be significantly impacted by fire and rainfall trends. So thinking about how we can take this code further and modify the code to calculate perhaps aerial mean NDVI from the NOAA CDR AVH-RR daily NDVI dataset. Or maybe whether we could add this as another interactive variable in the chart. So to conclude this, in this chapter, we understand and map the dynamic relationship between fire and rainfall and how this can influence conservation action and land management needs. We've begun by mapping burned areas to understand how much of and where the landscape is affected by burning. And following on from this, we understand how to access rainfall and calculate aerial mean rainfall and plotting this on a graph to understand patterns over time. By combining this and using our understanding of landscape dynamics, we can then begin to spot patterns in the landscape. This analysis, which would often be undertaken in the field or perhaps by hand or manually using satellite imagery, is made much more accessible through Google Earth Engine. Not only because we can perform this on a workstation that requires only an internet connection rather than computing power, but also because Earth Engine creates really quick, consistent results that we can update regularly to inform our conservation management practices. So if you have any questions about this code tutorial or the topic in general, please don't hesitate to email either myself or Chelsea Smith. Our emails are displayed on this slide. So thank you so much for watching and taking part in this tutorial. We really appreciate your attention and concentration, and we hope you've enjoyed learning about how to assess the spatial relationship between burned area and precipitation. Thank you.